Ladies and gentlemen, welcome to this webinar exploring the transition from analog to digital electronics in physics experiments.
The purpose of this webinar is to explain the different types of readout chains for the detectors used in nuclear physics applications. The webinar begins with a brief description of the fundamental concepts related to detector readout and then focuses on the comparison between the traditional readout chain, mainly based on a combination of different analog modules, and the digital chain, based on a single multipurpose module called waveform digitizer. The waveform digitizer samples the signal and produces sequences of waveforms, similar to any digital oscilloscope, and saves them into a memory buffer. The difference from commercial oscilloscopes is that the waveform digitizer designed for nuclear physics applications implements a multitude of online data processing algorithms that process the waveforms acquired by the analog-to-digital converters, ADCs, and extract the required synthetic information, such as energy spectra, time distribution, signal waveform variation, and more. There is a multitude of detector types for nuclear physics, each with specific characteristics that make them suitable for different applications. They can be broadly divided into three main categories. High-resolution energy spectroscopy detectors. Typically, these are semiconductor detectors such as silicon or high-purity germanium detectors, HPGU, that produce weak charge signals when traversed by a particle. With this type of detector, a low-noise preamplification stage is always necessary, usually a charge-sensitive preamplifier, CSP, often integrated directly inside the detector to maximize the signal-to-noise ratio. Medium-resolution detectors. This category includes the most common scintillators. In this case, the passage of a particle through the crystal produces a light pulse that is then converted into an electrical charge using a photoconverter, such as a photomultiplier tube, PMT, or a silicon photomultiplier, CPM. In certain cases, the converter already has sufficient gain to produce an electrical signal of hundreds of millivolts, so a preamplifier may not be necessary. Low-resolution energy detectors. Once again, these are scintillators coupled with a PMT or CPM. Due to their limited energy resolution, they are often used for counting, active shields, anti-Compton shields, etc. The electronics used to read them often consist of simple discriminators, counters, and, in some cases, time-to-digital converters. When a particle passes through and interacts with the detector, it produces a charge pulse, whose amplitude, duration, and shape depends on both the detector characteristics and the type of incident particle. Generally, the charge pulse is very weak and requires a low-noise, highly sensitive preamplifier, which is often placed very close to the detector or even inside it to minimize noise effects. There are various types of preamplifiers, but they can be broadly grouped into two categories. Charge-sensitive preamplifiers, primarily used for high-resolution energy spectroscopy applications. Their output is typically slow, on the order of microseconds, and does not faithfully reflect the input signal's shape generated by the detector. Fast, or current, preamplifiers. In this case, the preamplifier has a wide bandwidth and generally does not alter the signal shape. It produces a very fast output signal, on the order of nanoseconds, and is typically used in applications where timing information is crucial. In certain cases, the detector itself has sufficient gain to generate signals in the tens or hundreds of millivolts range, eliminating the need for a separate preamplifier. This is, for example, the case with some PMTs. Since these detectors are fast, their signals can be considered similar to those produced by fast preamplifiers. The amplified signal is then read by the readout chain, which aims to identify the pulses and acquire the necessary information for the application. Typically, the signal amplitude, in the pulse height analysis, PHA, or the pulse area, in the charge-to-digital conversion, QDC, is acquired to obtain energy information. In most cases, timing information is also acquired, in the form of time of arrival, rise time, time over threshold, etc., using a TDC. In other cases, information about the signal shape is needed to identify the type of particle or interaction. All this information is temporarily stored in dedicated memory buffers within the acquisition chain, waiting to be transferred to the computers running the data acquisition and analysis software, DAQ, which ultimately produces the desired results for the application, spectra, lists, statistics, and output files. After the data has been acquired, it undergoes further processing to extract significant physical information, including pulse shape, event correlation, and interaction position. This analytical approach is widely known as multi-parametric analysis, which yields physical quantities that characterize the interaction between matter and radiation. In the traditional acquisition chain, the detector signal, after being amplified by a preamplifier and brought to an amplitude level typically ranging from tens of millivolts to several volts, enters a series of mainly analog modules that condition the signal. These modules typically include shaping amplifiers, peak stretchers, charge integrators, discriminators, time-to-amplitude converters, etc. The output is usually either a quasi-static analog signal that can be converted by a slow analog-to-digital converter (ADC), or a logical signal that can be counted by a scaler or measured by a TDC. In this scheme, a significant portion of the acquisition chain relies on analog signal processing, with digital conversion taking place only at the end of the chain. As a result, there are multiple interconnected modules, each serving a specific function. Consequently, the system lacks flexibility, as one or more modules need to be changed when the required measurement type changes. Additionally, a setup constructed in this manner is often complex, requiring intricate wiring and manual settings that are difficult to manage and, most importantly, replicate. The fully digital acquisition chain takes an almost specular approach compared to the analog chain. While a preamplifier is still necessary to bring the weak detector signal to an appropriate amplitude level, the conversion from analog to digital is performed right after the preamplifier, without adding any analog signal processing, thus preserving the complete signal information. Sampling is carried out using a fast flash ADC, typically with a sampling frequency starting from 100 megasamples per second and exceeding 1 gigasample per second. The choice of sampling frequency depends on the signal speed, i.e., the detector response, as well as the type of preamplifier and the required measurement. The number of bits in the ADC also varies depending on the application, typically ranging from a minimum of 10 to a maximum of 16. A good compromise covering a wide range of nuclear physics applications is a 500 megasample per second digitizer with 14-bit resolution. The analog signal is continuously sampled and converted into a digital format without interruptions. The output of the ADC is a stream of data that is typically read by an FPGA. This continuous data stream is digitally processed using dedicated algorithms implemented in the FPGA firmware, aiming to extract the required information and measurements for the application. Therefore, we can say that the digital acquisition chain is capable of providing the same information as the analog chain, such as pulse height, charge, timestamp, pulse shape, counting, etc., but in a much more flexible, efficient, and compact manner. Unlike the analog chain, which consists of multiple separate modules, the digital chain has a single acquisition module, namely the waveform digitizer, within which various processing blocks are implemented, each providing specific information. The number of wiring connections is greatly reduced, as well as the physical footprint. Additionally, the functional blocks can be modified at any time through firmware upgrades. Parameter settings are done through registers, making them fully controlled by software and reproducible at any time. As mentioned, the flash ADC continuously samples the signal and outputs a high-rate data stream. For example, a 16-bit ADC with a sampling rate of 500 megasamples per second has an output data throughput of 1 gigabyte per second. There are very few applications where it is necessary to acquire and save such a massive amount of data to disk. In most cases, especially when dealing with multiple acquisition channels, a triggering system needs to be implemented to define regions of interest and acquire data only within a certain time window. There are two different triggering scenarios. Common trigger. In this scenario, there is a trigger that is common to all channels either from an external source or from a combination of the channel self-triggers, and defines an acquisition window of a certain length. All channels receive the common trigger and save a certain number of samples around this trigger in a local memory buffer. Typically, in this mode, called oscilloscope mode, the acquisition is limited to saving portions of waveforms, so sequences of raw, unprocessed samples. The readout software then reads the waveforms and saves them to disk or computer memory buffers, where they are processed offline to extract the necessary information for the specific application. The data throughput to the computer is now much lower than the output from the ADCs, but it can still be high, especially if the trigger rate is high or if the acquisition window is wide. Self-trigger: each channel independently acquires data, creating its own self-trigger when it detects the presence of an incoming pulse. An algorithm for pulse identification, such as baseline restorer, digital discriminator with a threshold, etc., is necessary. Once the pulse is identified, a local trigger, valid only for that channel, is activated, opening a certain acquisition window that can also be retroactive, thus saving a certain number of samples that arrived before the trigger. In many cases, the required information for physics analysis is not the complete waveform recording but only specific characteristic parameters such as pulse height, charge, timestamp, rise time, etc. Therefore, it is possible to implement algorithms in the FPGA that process the pulse waveform and extract these parameters. This acquisition mode, called digital pulse processing, DPP, allows for list mode acquisition, where only the list of parameters extracted from the pulse processing is saved in the board's memory buffers, without saving the raw waveforms or saving only a part of them. By acquiring in list mode, the data throughput from the board is significantly lower compared to reading the waveforms, making it possible to acquire pulses at very high rates. Of course, there are also intermediate situations between the oscilloscope mode and the DPP mode. For example, it is possible to utilize DPP algorithms only for pulse identification and generating a channel trigger, which is then combined with triggers from other channels using appropriate trigger logic, coincidences, multiplicities, etc. to generate a global trigger that opens the common acquisition window to save waveforms on all channels simultaneously. Similarly, it is possible to acquire in list mode with DPP, where channels acquire on independent self-triggers, but with a common validation signal for all channels or groups of channels, allowing to save the list data only if it belongs to a certain time interval. This approach enables the implementation of coincidence logic, veto logic, etc.
The first section of this webinar is now completed. Stay with us for the second part.